So next up, from axiomatic probability, we're going to look at expected value. So the expected value of a variable, remember a variable is associated with a sample space that has a probability distribution, and that S is numerical. These tags are real numbers. And given a real function f, we can form a new sample space, SF, which is f applied to those tags. And we have therefore the same probability distribution. Expected value is just the T1 times P1 up to TR times PR, and that's a definition. We sometimes write it like this. If f is associated with SF, then we've got an expected value of f of x also, defined similarly. And we very often denote it like this, which suggestively looks a little bit like an integral. Now, expected value of a function, let me elaborate just a little further. A function is defined for each tx and s, and if x is a random variable, a variable associated with s, then y equals f of x is also a random variable, but the sample space is now the image of the original sample space. So we denote it y1 to yx to yr, where y sub x is equal to f of x. The expected value of y would be x equals 1 to r of y of x px. The expected value of f of x, therefore, is x equals 1 to r f of tx times p of x. Let's look at an example. Suppose we have 6 outcomes of a die, and our sample space is numerical. S equals 1, 2, 3, 4, 5, 6. And if the die is fair, then we have a probability distribution that's uniform, 1/6, for all outcomes. The expected value is 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4, so on and so forth. But that is just 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6. 21 over 6, or 7/2, or 3.5. But notice that even though we ended up with an average, it was only because the probability distribution is uniform. An unfair die would have led to a different expected value. And x squared would be associated with the sample space 1, 4, 9, 16, 25, 36. The expected value had been the average of those numbers, which in this case is 91 over 6. Or equivalently, we could use our definition of expected value of a function of x, and we end up with 1/6 times the sum k equals 1 to 6 of k squared. There's a formula for that sum. If we apply it, we get 91 over 6 again. So a natural question is, what is an expected value? We know what it is if we have a uniform probability distribution, all probabilities the same, it's an average. But in general, we're using the axiomatic approach. So we're going to first establish properties of expected values, and then we'll use the properties to interpret them. So what kind of properties do we have? Well, if we've got x and y associated with s, with a given probability density distribution, then expected value is linear. So the expected value of alpha x plus beta y is alpha expected value of x plus beta expected value of y for all alpha and beta in R. We'll prove this later. Notice we often denote the expected value of x by mu, mu signifying a mean of some type. It's also easy to show that the expected value of x minus mu is 0. I'll leave that as an exercise. The variance of x, denoted var x, is defined to be the expected value of x minus mu quantity squared. And variance has many properties of its own, as we'll see next. So first off, the variance, by definition, is the expected value of the quantity x minus mu squared. And we expand the square. We use linearity to separate that into separate expected values. Notice the expected value of mu squared is just mu squared because it's just a number. And that gives me expected value of x squared minus 2 mu squared plus mu squared. That's the expected value of x squared minus mu squared, and that gives us expected value of x squared minus the expected value of x quantity squared, and that's our first property. The variance of x is the expected value of x squared minus the quantity, expected value of x, quantity squared. The variance of alpha x is, by definition, given like this, and we can factor out the alpha squared, and we end up with the variance of alpha x is equal to alpha squared with the variance of x. Now, joint probability, if we have two variables, the expected value is defined, but now we have to use two sums just because we have two indexes. Let's go back to our linearity property. So we have actually a joint probability because we have two variables, x and y, but then we can split this into two different sums and regroup. And notice that in the first part of the expression, we have the sum over y of p of xy, but that's just the marginal distribution of x, of little x. Similarly, we get a marginal distribution of y, and that gives us alpha, the sum t of x times the probability of x, plus the beta times the sum of the y's, use of y times the probability of y's, but that's just our expected values. Now, let's continue and prove something very useful. If x and y are independent, then the expected value of their product is the product of their expected values. And this comes directly from the fact that if x and y are independent, the probability distribution, joint probability distribution, is the product of the individual probability distributions. So we take the expected value of xy. Well, that's the sum x and s, y and s, tx, uy, p of xy. That, on the other hand, can be the joint probability is the product of the individual probabilities. And we regroup, and we get the expected value of x times the expected value of y. So this is a useful result. Notice that if x is associated with 0, 1, for example, with a probability density of 1/2, 1/2, the expected value of x is 1/2, no surprise there. And if xy is associated with 0, 1, then of course this would also be the expected value of y, because it's just another variable with 0, 1 with the same probability distribution. But the pair x comma y would be associated with this space, 0, 0, 0, 1, 1, 0, 1, 1, and each would have a probability of a fourth. So x times y would be 0, 0, 0, and 1, and the expected value of xy would be 1/4, which is the product of the expected value of x and the expected value of y. So suppose that x and y are independent variables. Their variance of their sum is by definition this expression. We can square the quantity on the inside of the expected value in the first one, and notice that by linearity, the second we get expected value of x plus expected value of y, that quantity squared. Squaring that gives us this very long expression. We can rearrange that, and notice we now have the expected value of x squared minus the expected value of x squared plus the expected value of y squared minus the expected value of y squared plus 2 times the expected value of xy minus the expected value of x, expected value of y. The first one is the variance of x, the second one is the variance of y, and the last one, remember x and y are independent, So that's 0. So that leads to the variance sum law. If we have n variables associated with S with the same probability distribution as X, they're identically distributed. And suppose that each of these variables x sub I is independent of all the other variables xj, then the variance of the sum of the x's is the sum of the variances of the x's. To prove it, we notice it's true for n equals 2. That's the previous slide. For the n plus 1 case, we let y be equal to x1 sum up to xn. The variance of y plus xn plus 1, well, y is independent of xn plus 1 because all the x1 up to xn's are independent of xn plus 1. So we get from the previous slide the variance of y plus the variance of xn plus 1. But the variance of y is, by the induction hypothesis, the sum of those variances. So that leads us to the definition of a sample of a variable x associated with S. It's a set of independent variables, x1 and xn, each with the same probability distribution as x. We say that these x1 to xn's are independent and identically distributed, often abbreviated IID. Each x sub I has the same mean, mu, and variance, sigma squared, is how we're going to denote it as x. So this standard deviation in x is defined to be the square root of the variance. The sample mean is just the average of these n variables. And notice that the sample mean is associated with this v sub s, which is all the alpha 1 t1s plus alpha r trs, where alphas are real numbers, often called the vector space of all linear combinations of elements of S. For example, a 10 would be the average of 10 rolls of a fair die. And every different set of 10 rolls would give you a different value for A10. So notice we have now that if we have IID variables associated with S, then each x sub I has the same mean, the same variance, sample means defined this way. The expected value of AN is the expected value of 1 over n of the sum of the x's, which is 1 over n times the expected value of x1 plus up to expected value of xn by linearity. And we get that, which is mu added to itself n times, but that's just mu. The variance of A sub n is the variance of 1 over n times the sum of the variables, but that's 1 over n squared times the sum of the variances. The variances of each is sigma squared. There's n of those, so we get 1 over capital N sigma squared. So these are two properties of the sample mean. Now, if we sample a random variable, we end up with what are called n trials of x, resulting x1 up to xn. A sub n is the sample mean, or the average. Let's consider what this means intuitively. If we perform n independent trials, that's a sample. And notice that practically it means that we always have to sample from all of S. So if we choose a number from S, t sub x, then we have to put it back in before we do another sample. This is called sampling with replacement. So t sub x occurs approximately p of x n times, t1 occurs p1 of n times, t2 p2 of n times. And so therefore a sub n is p1 of t1 plus up to px tx up to pr tr approximately, and that's the expected value of x. That's mu, like we saw. So if E sub n of x is another notation for the average over n trials of x, then it may look like this or like this, but regardless, we know we can rearrange it. So that it looks like all the t1s first, all the t2s second. Well, there's about P1 n times that we get a T1, and P2 n times we get a T2, and so on and so forth. And this is approximately, and therefore we get essentially T1 P1 plus T2 P2 up to TR PR, where we have the n's. The n's cancel, and that's approximately the expected value. And it becomes exact as n goes to infinity. If we had another m different trials of x than the expected value, rearrange it, and we get essentially the same proportions of T1s, T2s, up to TRs, approximately. And we can factor out the m and cancel, and again we get approximately the expected value of x. It's exact as m goes to infinity. So let's look at this sample mean versus the theoretical expected value. The sample mean is the average over n samples. The expected value is the sum x equals 1 to r of t sub x p of x. There is no n there. In other words, this is what we expect as we let capital N go to infinity in the sample mean. For example, suppose we have a class of 100 that takes a test, 30 get a score of 70, 60 have a score of 80, and 10 with a score of 100. If we randomly chose a student from that 100, the probability we'd get a student with a 70 is 0.3, a student with an 80 is 0.6, and a student with 100, 0.1. The expected value, therefore, for the class is 70 times 0.3 plus 80 times 0.6 plus 100 times 0.1. That's a 79 average for the class. Now suppose we did 1,000 samples from this class. Remember, we're doing sampling with replacement, so we can do 1,000 times we independently choose one of the students and record their test score. 70 occurs about 313 times, or theoretical would have been 300. 80 is 580 times, theoretical would have been 600. And 100 occurs 107 times, theoretically we would have had 100. Would have had 100. So the sample mean is the average over these 1,000 samples is 79.01. So let's compare further. So we have theoretically a variable x associated with a set S with a probability distribution over a sample of size n. We have trials, x sub I. The theoretical expected value is defined in terms of the elements in the sample space and the probability distribution. The sample mean over trials is the average for those trials. The variance is defined, denoted by sigma squared, which is the standard deviation of x, defined this way. The sample variance, similarly, is defined to be little s sub n squared, where that's the sample standard deviation, and is the sample average of x minus a sub n, the x sub I trials minus a sub n squared. So let's tie all this together using what's called the law of large numbers. So we have the expected value of the sample mean is mu, and that means that the sample average is close to the expected value, but how close? Well, for large n, it's about sigma over the square root of n for the expected value on average, and that quantity goes to 0 as n goes to infinity. It's not a proof, but it does kind of give us some idea of what's going on. The law of large numbers says that the sample mean, e sub n of x, for large n is approximately the same as the expected value of x. And for any set of samples of size n, the sample average approaches the theoretical expected value as n goes to infinity. So let's look at an example. If we have a function that's real valued, and the law of large numbers is going to also imply that the sample average of the function of x converges to the theoretical expected value of f of x as n goes to infinity. So for example, suppose we define a function chi sub a of v, which is 1 if v is in the set A and 0 if not. The sample mean is just the average over chi sub a applied to each of the trials. And that's 1 over n times the sum of a bunch of ones and zeros, which forms a count of the number of occurrences of A in n trials. So the C sub n of A is the number of occurrences of A in n trials, means that the sample mean is C sub n of A over n. The theoretical expected value of chi sub A of x is the sum over the x and s of chi sub A of t of x p of x. But chi sub A is 0 if we're not in A, so it reduces to this sum. And chi sub A of t of x is 1 when we're in A, so therefore we end up with the definition of the probability of A. In other words, the law of large numbers says that the probability of A is the limit as n goes to infinity of the relative frequency. So in summary, the axiomatic approach to probability is all we need to develop all of probability theory. And we used it to develop the concept of expected value. And we used it to justify, but not yet prove, the law of large numbers. An expected value, in turn, interprets and connects to applications the axiomatic approach to probability. In fact, very often when we're using probability, we're actually applying the concept of expected value.